Hi everyone, my name is Lulu, and this is my final project presentation for computational photography on single-shot direct and non-line of sight imaging via speckle correlations. The goal of this project is to reconstruct an occluded object by leveraging the statistical properties of laser speckle photography when using an incoherent light source. On the bottom of this slide shows a diagram of the schematic setup, where a laser goes through a vibrating diffuser which enforces the spatial incoherence assumption, goes through an object and a scattering medium to be imaged by the camera. The object I use is cutouts of a black sheet of paper, and the scattering medium is a thin sheet of a napkin. So when spatially coherent light passes through a scattering medium, the medium will randomly scatter the light and distort the final image that's captured by the camera. However, when spatially incoherent light, like the laser used in this project, passes through a scattering medium, it will scatter the light in a way that preserves the properties of the object that it passes through. The statistical property that's leveraged in this project is called the memory effect, which states that nearby points on an object are scattered by the scattering medium to produce highly correlated, shifted, random speckle patterns on the camera. This means that any minuscule shifts of the laser's angle towards the camera will result in shifted versions of the speckle pattern. This is shown in the video on the right-hand side here, where I'm shifting the laser in multiple directions very slightly, and it results in shifts of the speckle pattern on the lens of the camera. So the two types of imaging setups I use are shown here. The first is the direct imaging setup, which was also shown in the previous slide. In this, the laser, object, and camera all lie on the same vertical and horizontal planes, and the laser's beam passes in a straight line through all of these parts. For the non-line of sight imaging setup, the laser's beam passes through the object and then reflects off of a surface through a scattering medium and is finally imaged by the camera. So the direct imaging setup has applications in the medical field, such as imaging blood cells through biological tissues, and the non-line of sight imaging has applications in things like the robotics sector to aid in seeing around corners or providing environmental cues that aren't available with traditional RGB imaging techniques. The overall pipeline for the reconstruction algorithm is as follows. We have the camera image of the speckle patterns I of theta, and the goal is to reconstruct the original object O of theta. The first step is to perform object autocorrelation of the camera image I of theta. And this could look something like this. We do this because due to the memory effect, the autocorrelation of I of theta should be approximately equal to the autocorrelation of O of theta. Here I say approximately equal because the right-hand side is actually missing a part of the equation, which is S of theta, representing the speckle intensity pattern. However, the speckle intensity pattern's autocorrelation is a sharply peaked function that when it's convolved with the object intensity O of theta, it outputs approximately O of theta. The second part of the algorithm is to perform an iterative find-up type phase retrieval algorithm. And this iterates between the Fourier domain and the object domain in order to satisfy the Fourier domain constraints and the object domain constraints. And this uses the magnitudes of the autocorrelation to find the per pixel phase intensity. Phase retrieval was ran with multiple beta values, which is a constant in the algorithm, and I used the ones that yielded the best reconstruction results, which are shown here. So both of the imaging setups were tested on two different objects, the triangle and the square one, and also the one with the oval in it. And here I'm just showing the best results for each case. So for the direct imaging case, the autocorrelation of the object O of theta has a sharp peak in the center with two peaks on either side, and the autocorrelation of the image I of theta follows a similar pattern where there's a sharp peak in the middle and slight peaks on the left and right sides, although it is a little bit noisier and hard to see those additional peaks. The reconstruction doesn't look exactly like the original object, but we can kind of tell that the algorithm is able to pick out that there are two distinct shapes in the object. For the non-line of sight case, the autocorrelation of the object is a oval shape, and the autocorrelation of the image follows the same kind of shape as well, where it's longer in the vertical direction. The reconstruction is able to retrieve this oval shape, although a little bit noisily, and it is located in approximately the correct location on the image. So these results aren't perfect, and it's due to some limitations in my setups, including, first of all, the distances between the object camera and laser were a bit large. They were on the order of centimeters when some of the reference papers were on the order of millimeters or micrometers apart. And secondly, I had to physically hold up the scattering medium when imaging the IF theta images, and this could have caused some additional noise. So that's all I have for you. Thank you for listening.